Okay, in this lecture, we're going to talk about how a breath is delivered in a ventilator. Right, so that's going to be chapter 3 in pilbeams. I hope you enjoy it, and I am going to enjoy it because I love this subject, and also it'll be one step closer to getting this week's voiceovers done. So this is a very important concept that you're going to need to understand prior to being able to understand ventilators and how they work. When you look at the equation of motion, so muscle pressure plus ventilator pressure equals elastic recoil pressure plus flow resistance pressure. Oh my God, that sounds terrible, right? That's really not when you start to think of breaking it down into a different language. That muscle pressure, that's what the patient can generate it, plus the ventilator pressure, should be equal to what the elastic recoil pressure or your compliance, right? Uh, and then the resistance. Not too bad, right? Um, compliance and resistance going. You need to be equal with muscle pressure and ventilator pressure to equate to a normal blood gas. Not too bad, right? We figured it out. Good job. Well, dang it, I answered some of that in the slide before. So the motion is in the lungs, right? The ventilator can be the main source or the full source. The patient could be the full source, or you can have a combination of the two, right? So that's when we start to think of SIMV with pressure support or something like that that's going to allow the patient to do some of the work and the ventilator to do some of the work. And then the rest is compliance and resistance. Okay, remember our resistance is a change in pressure divided by a change in flow, and our compliance is the change in volume divided by our change in pressure. So we're going to get some really good thought processes of understanding of why these pressures, what they mean, and what they do with the ventilator and with the patient generating them by themselves. So there's things that we're going to look at, like our transrespiratory pressure, our transthoracic pressure, and transairway pressure. So these are all very good concepts. Remember, chapter 3 is going to cover some of this stuff. As we learn to set ventilators, we're going to realize that the practitioner is going to be setting the mode to deliver a pressure or volume. Okay, well, that pressure or volume has 4 different variables or control variables. That's going to be pressure, volume, flow, and time. So when you look at the front of the ventilator, you're going to see on the screen, it's analyzing the pressure, the volume, and flow, and those are graphed out over time. So very big concepts and very confusing to practitioners who've been in the field for quite a while as these graphics popped up. There are things that they weren't used to seeing at all. So they had to all learn that years and years and years ago. And now here you are learning it as a new grad. Pretty cool. It's the circle of life. I'd sing for you, but it's awful. One of the things I want you guys to remember is as I start talking about these things, you're going to be like, you may feel like this is awful rudimentary. This is very basic. I already get this concept. That's okay. Hang on. It's going to get better. But just be patient with me. We're going to go through this stuff in stages to make sure that we have everybody carrying along. Okay. Pressure control ventilation. Breath delivers a pressure to the airway resulting in a volume. So the practitioner is setting a pressure control. So an inspiratory pressure, right? Kind of like on a BiPAP is inspiratory pressure, but we call it a pressure control on a ventilator. So say they're setting that at 20 centimeters of water pressure. What volume is that going to generate? Are you thinking? You should be thinking. Well, the problem is we have no idea, right? Because we don't know what the compliance and the resistance are. So once we put that pressure in there, based on the compliance and the resistance, we'll generate a volume, and that specific volume will come up on the screen for us as an exhaled volume, and that will give us an idea. And then we can look at their compliance and resistance on there. Okay, a volume controlled breath. This is going to be a descending ramp looking thing. So when you go on the top square, you look at number 2 on that top square. That is a pressure measurement, right? And it's over time. And so we're putting that's the pressure that's being generated in the volume mode. So that pressure's coming in, it's peaking up, and it's reaching about 38, I guess it looks like. And then it's once that volume comes in and it peaks, the patient begins to the flow pattern starts to decrease and comes back down to baseline. So you look down at the bottom and you can see the volume going in and when it drops off. The big difference between volume and pressure, we're delivering a set volume, say 450 in this case, or 500, and then it's generating a pressure. And that pressure is a variable based on compliance and resistance. Flow is how fast the air is going to get there, right? Well, this is rarely used, but it is utilized in some ventilators to help to reach a patient's volume, right? Or pressure, right? Now, it's always used, it's just not a mode, right? So a flow of 60 liters per minute is a normal standard where we start to set our patients on, and we'll adjust it off of that based on what the patient's needs are. Why 60 liters? Well, because we used to have to calculate everything by hand. So if you have 60 liters per minute, that's 1 liter per second. So you can start to calculate these things a little bit easier based on easy numbers. Then we think of I time down the road. We'll talk about I time. Well, 1 second I time and 60 liters per minute, that makes math really easy. So that's why we did it, not because that's what the patient needed, right? Now ventilators will analyze this stuff for us and make it better. However, this is why and how that started. So you get a history lesson too. So you can put money in my tip jar when I get a tip jar. So the flow is being pushed to deliver a volume. So if you think flow equals volume divided by time. So now think about this, the flow times I time will generate a volume. That's math. So time control is very rarely used. When you look at time control, you think about the rate, whatever the rate is. So say you have a rate of 10. Well, 10 goes into 60 seconds, 6 times. Every 6 seconds, that breath will be delivered. Okay, that's it. Just delivered based on time control. Okay, so the trigger, patient triggering, for where we are in this class, we're going to have a whole lecture on this down the road. So for where we are, the trigger is what starts the breath. So the patient can generate a breath by a negative pressure, a negative flow, or a negative or positive volume, I guess, triggering back a volume to trigger. They don't use volume triggering very often, but pressure trigger and flow trigger. Flow trigger is probably the most common right now, but now we have an electrical stimulus trigger as well, which would be a knob by servo maquette. Limit variables. So this is what stops the breath from happening, right? Or stops it at the end of its cycle, right? So pressure limiting, if I set the pressure to 30 centimeters of water pressure, it will stop at 30 centimeters. This is in a pressure control mode. So I set it to 30, the flow goes in until it reaches that 30 centimeters of water pressure and then stays there or stops the breath, right? Volume limiting, the breath is actually going to go into the patient or, out of the ventilator. And once it reaches 500 milliliters, if that's what I set, the ventilator is going to stop at 500 ml. So it's not going to go any further. So it's limited by that 500 ml factor, right? And then flow limiting, the flow is set to what you'll get. So if I set 60 liters on there, I want to have 60 liters go to that patient. 60 liters go to that patient, and that's what they get. So now that may be a variable on there, but just an example. So this is one of those things where when we get talking about this, the vernacular or the actual verbiage that we're using in respiratory sometimes is not congruent with what nursing or another career field is utilizing. So therefore, it makes it confusing. So when we say pressure limiting, it's going to sound a little bit confusing, right? So pressure limiting will limit that pressure at that certain setting, right? But max safety pressure is typically 10 centimeters above the pressure limit. So if I set the pressure limit at, say, 35, I set the pressure control at 30, I set the pressure limit at 35. Say if the patient coughs at the end of that inspiration, it's going to peak the pressure, right? So your peak pressure is going to skyrocket. If that happens, the ventilator does not want that pressure to go higher than what it's supposed to. So there's going to be the alarm setting, and then somewhere usually around 10 centimeters above that is the actual limit, the max safety pressure limit, that'll pop off and it'll start to dump the gas flow. There's also an internal pressure safety pop-off that's set by the manufacturer, and it is typically set at about 120 centimeters of water pressure. Now, that would shred just about any lung tissue. However, it's there to protect the patient from having a sustained pressure at 120. Time cycle ventilation. If the inspiratory phase ends when a predetermined time has elapsed. So the ventilator's got this mechanism within it that, and remember this is on different ventilators, we'll have different cycles. If I have that rate set at a certain, we used a rate of 10 before, is every 6 seconds it's going to cycle. So that timer stops, hits that 6 seconds, and it stops the breath, right? That breath is canceled. And then the patient goes into exhalation, then there's a pause phase, and then an inspiratory phase again, right? So it's all set up on a timed cycle. Flow cycled ventilation. This is being used all over all different platforms. It's the most common cycling mechanism in the pressure support mode. And what happens is we set an expiratory, like percentage or a predetermined value for exhalation. So as the flow starts to decrease, that ventilator will cycle into exhalation, causing that patient to be able to relax, exhale, chill. our pressure cycled ventilation is just that. I mean, we kind of talked a little bit about it a bit ago, but inspiration ends when a set pressure threshold is reached at the mouth or upper airway, or end of, at the ET tube, whatever. The exhalation valve then opens and exhalation begins. We don't want that pressure to exceed what it is that we set, so the ventilator sees where it's set and then releases and goes into exhalation. All right, the expiratory phase definition, not when the patient dies, but the expiratory phase encompasses the period from the end of inspiration. So there's inspiration and then there's a pause, right, typically, and then it goes into exhalation. So that from that end of inhalation on to the next breath. Right now, remember, if we're doing an inspiratory hold, and what are we doing an inspiratory hold for? We're trying to find a plateau pressure, and so if you do that, you're holding inspiratory. You're not. That's not a. That's not cycling into expiration. So that sounds like a good quiz or test question. So note the slide 16. Note if inspiratory hold is used, expiration is delayed. It may change your timing. Bass, how low can you go? Death row, to what a brother know. Hey, baseline pressure is just a peep. When you set PEEP on a ventilator, that is what the baseline pressure is going to be. If you had an ET tube that was disconnected from a ventilator, there's no ability for the patient to maintain PEEP because it's open foramen, so that PEEP would be 0 or ZEEP. It's called ZEEP, zero end expiratory pressure. And if the positive pressure is labeled positive end expiratory pressure on the ventilator, you'll hear PEEP. You'll see CPAP in a CPAP machine. And negative end expiratory pressure is that used to be a way that we would pull things out of patients, pull the exhalation out of a patient with NEEP, negative end expiration. So pretty cool stuff. So like I was saying in the last slide, NEEP was used by physicians, typically neonatologists, and it was thought that NEEP could reduce resistance and help the patient exhale better, which kind of makes sense, but that led to alveolar collapse. So then that made it fall out of favor, and now we use a positive end expiratory pressure to shunt open the alveoli. So now a giant thought process on this whole from this whole slideshow thing is the difference in types of breath. The big one, spontaneous, would be triggered by the patient. The patient can generate that breath by himself or his or herself, depending on their needs. And then mandatory, the ventilator is cycling based on a time cycled, time triggered breath. So every so many seconds, that breath is going to cycle on a predetermined rate. So that's the big difference of the two of them. I see some of you are working on your amazing, because if you're always trying to be normal, you'll never know how amazing you can be. See what I did there? I just kind of made fun of you a little bit. All right. Lecture's over. Do your discussion board. Take care.